Okay, so welcome to you all to the class lecture. Today will be the 9th lecture. So lecture 9, the virtual work, D'Alembert's principle. Simple and equation of motion. So this is the topic we'll consider in this lecture, and let me remind you, we have started this in the last lecture. So let me recap a little bit about the last lecture. Last lecture we have started with this virtual work and D'Alembert's principle. So let me review, and we came up to certain equation. So we'll write down those equation, and for the derivation we'll follow from there. So just a recap of last lecture. So virtual work or virtual displacement, we define that the displacement in the system which is consistent with the forces and the forces of constraint, and it happens instantaneously. So virtual meant, so this two important thing is consistent with the forces, and constraints. So this is the first point, and second point is it happens, it doesn't take any time. To happen. So it's instantaneous. So virtual displacement is a instantaneous process, doesn't take any time, and difference with the real displacement, it occurs in a finite interval, and during that interval force can evolve, constraint can change. So it is complicated. So you have to consider the change or the evolution of the forces with time, even during the small interval. But virtual displacement, we are imagining something happening, and some displacement in the system which is consistent with the forces and forces of constant, as well as it doesn't take at the time. As I mentioned in the last lecture also, that when the force of constraints are not known a priori, and you have to consider the effect of those, then this virtual displacement or virtual work done will be helpful. So we discussed static as well as a dynamic system, and the D'Alembert's principle was that virtual work done, so virtual work done by the force of constraints are 0. So this we consider to find the equation of motion for the system having constraints. So D'Alembert's principle is the virtual work done by the force of constraints are 0. So this is the principle. Based on this principle, we'll work out and find the equation motion for the system. So we consider in last lecture first the static situation, and we obtain after putting the D'Alembert's principle that Fi applied force times the virtual displacement, and this is the work done, virtual work done by the applied force will be 0. So this was the in the static situation. And this was, if you look at my last notes, this was the equation 4. Okay. So this is the principle of virtual work and for static system. But if we consider that, we consider last time also, if we consider the dynamical situation, that forces are not zero at the equilibrium, but we have a dynamical situation, and again we apply the principle of virtual work or D'Alembert's principle, and we came to this stage, that equation 9 in the last lecture. So it is applied force on the ith particle minus the rate of change of momenta, and dotted with this virtual displacement, this work done is 0. So this is D'Alembert's principle or consequence of D'Alembert's principle. So using this, today we will find the equation of motion. Note, this is our equation 9 in the last lecture. Okay. So now today's lecture is starting from this equation. So now we'll make a change of, so we have the real coordinates. Real coordinates are, say, are I, the set real coordinates I equal to, say, 1, 2, if you have n number of particles n. Now we assume that there are from here we can go to a set of independent variables, or that we consider, you can consider as generalized coordinate. But this D'Alembert's principle for static as well as dynamical case says that all Ri are not independent. From here we go to another set of independent variables. Okay. So set of independent variables. So naturally, so let me write with the j. So j can run 1, 2 to n, and naturally since the constraints are present, so your n should be less than capital N. Okay. So this we have to keep in mind, that number of variables Ri is more, and number of independent variables, because there are certain constraints, constant will reduce the degrees of freedom. So this and these are your generalized coordinate. Okay. Okay. So now if we go from this to this, so let us consider Ri is function of this variables and time, right. So now Ri are function of the Q's, which are independent variables. Okay. So naturally, if we use the differentiation chain rule, we can find that so this let me denote the equation number. So Ri are basically function of, so this is my equation 10, because I will refer this equation, and also in the discussion forum you can ask question in reference to the. So let us define the velocity. So Vi, which is dri dt, total derivative with respect to time to this variable. Now in the left hand side, Ri is function of independent variables Qj. So we can use the differentiation chain rule to find this differentiation. So this will be del Ri del Q, say, j and Qj dot Qj dot, and this is vector, this is vector, and j will be sum over 1 to small n, plus there will be time dependent, so del Ri del t. So let us denote this equation is 11th. Okay. So we will come back, we will be using this equation, we will put this equation in the D'Alembert's principle, that virtual work done by all force of constants at 0, to find the equation of motion. Now let us consider the equation 9, that is the D'Alembert's principle, and would simplify each term. So it has two terms, so let us consider first term. So first term in equation 9, is sum over I F I A, that is the applied force, times delta R I, sum over I equal to 1 to n. So only when we have the q variables, then sum over 1 to small n. So okay, before that we can also write, before coming to that I forgot that before coming to that we can write the delta R I, the variation of the coordinates will be because R I are now function of Q I, right. So independent variable. So this will be delta R I delta Q J delta Q J plus delta T times something, but as we mentioned that for virtual displacement no time is taken, so this delta G should be 0 for virtual displacement. Okay. So now this is 0, so this we denote by equation, this we can denote by equation 12, yeah, this denote by equation 12. Okay. So now we will use this equation 12 in this to simplify the first term in equation 9, that D'Alembert's principle. Okay. So the first term in equation 9, so let us substitute I equal to 1 to n F I A dot. So you remember we are dealing with vectors, so dot delta R I is delta R I delta Q J and delta Q J, sum over J, and sum over J is 1 to small n. So you have to be careful. Okay. So this I can write sum over I, sum over J and F I A dot delta R I delta Q J, so times delta Q J, which is sum over J, I will write J 1 to n times Q J delta Q J, where Q J I have defined as sum over I. So this quantity is your Qj. This quantity I define with the sum, with the, and this together is defined as Qj. So Qj, let me write here, Qj will be F I A dot delta R I delta Qj and sum over I 1 to capital N. So let us denote. So this is my equation 13, and maybe we can okay, and this may be 13 prime, because 14 equation I have denoted something else. So this equation, and we'll see that we call this new quantity as generalized force. Fa is the actual force, and now when we define like this for all particles, so this is the generalized force in the system. Okay, good. So now this is the first term. Now we will simplify the second term in the D'Alembert's principle. So let us in the second term. So concentrate on the second term. Okay. So second term we will consider, right, exactly. So it is sum over I Pi dot delta Ri with a minus sign in that expression, D'Alembert's equation. So this we can write as sum over Mi Ri double dot with rate of change of momenta. So we are writing with this acceleration kind of thing. So delta Ri. So this is your vector, this is your vector, okay, and sum over I 1 to capital N. Now again we substitute your delta, substitute this delta Ri from equation 12. So note that the equation, this is my equation 12, and I substitute this back in here. So this will give you sum over I 1 to N, sum over j, it's 1 to small n, and Mi Ri double dot del Ri del Q j delta Q j. Okay. Okay. So now we will calculate this quantity for mathematical convenience. We will calculate this quantity along with this sum separately. Okay. So let us focus on this term. So the sum over j and delta Qj we keep aside. So focus on the term sum over I M R I double dot into del Ri. So this is vector, and delta Q j. Okay. And this term we can after a little bit of rearrangement, I can write that sum over I ddt of M I R I double dot no M R I single dot. So let me erase. So dotted with del Ri delta Q j and minus. So when I take a derivative of this quantity, the first term Ri dot will be differentiated, which I will get the first the term which is my actual term. So I have to subtract the additional term, which is M Ri dot ddt of del Ri del Q j. Okay. Okay, so this fine, and we also denote this equation, I forgot to name this equation as 14. So, this equation 14, some part we are simplifying. Okay. Okay. So, now I have to calculate this ddt. So, now I will focus how to calculate ddt of del Ri del Qj. Now, del Ri del Qj is function of independent variables q1 to qn and t. So, I use the differentiation rule, chain rule of differentiation. So, this is also function of q1 to qn. So, let me sum use the partial differentiation rule. So, del q say k del Ri del Qj and Qk dot sum over k equal to 1 to small n plus del t partial derivative with respect to time. So, del Ri del Qj. Okay. So, this using the chain rule of differentiation. Okay. So, now let us simplify this equation a little bit of this quantity I will write. So, sum over k, which is 1 to small n, and then del 2 Ri del Qj del Qk plus del Qj del Ri del t. I interchange the partial derivative among these. So, this we get. Okay. This is straightforward simplification. And now, if I take del q derivative Qj derivative with respect to Qj outside. So, this will be del Qj times del R. So, these are vectors, we should not forget. Okay. Okay, del Ri del Qk, and there is a sum over k 1 to small n plus del Ri del t. But the quantity in this bracket, the quantity within this bracket is nothing but the and I am missing the one term is missing, Qk dot. So, here I missed Qk dot and Qk dot. So, the quantity inside the bracket is nothing but R dot, Ri dot. This quantity is nothing by R dot by equation. There is also earlier we have seen the equation. Let me show you this equation. Yeah. So, this is Ri dot. So, equation 11. So, this is Ri dot. Okay. So, now we will use that equation 11. So, let me write for completeness of the note, see equation 11. Okay. Okay. So, so this is basically, so we obtain a important result that ddt total derivative ddt of del Ri del Qj is basically del Qj of Ri dot. Okay. So, this is another equation and we name this equation as 15. So, So this is our equation 15. This will be using, this equation will be using in here, in this expression. Okay. Okay, so let us continue with our derivation. You have to keep patient because this is little bit mathematical derivation, so don't forget this dot. Okay, so this also we can write d dt of del r I bar del q j equal to del v I or del q j. So this will substitute in that equation I said, you just will substitute in equation 14 in this no, not 14, will substitute this in the simplification of this equation 14, this here. Okay. Okay. So let us proceed. Also from equation 11, look at the equation 11. Equation 11. So equation 11. If we Vi, if we differentiate this del Vi with respect to q j dot, you will get del r I del q j. So this is also, you just differentiate equation 11 and so let me write this equation again in the form and give another number, that will be easier. So we obtain del V I del q j equal to del r I del q j. So these are the two equations which will be substituting in the D'Alembert's this equation 14, that D'Alembert's principle. Okay. So let me this will not able to finish this derivation in this class. So let me review what we have done in this class, then we'll continue with this derivation in next class. And we are almost there. In 5-10 minutes we'll find the equation of motion. So in this class we started with that constraint imposed two type of problem. One problem is that all coordinates are not independent, so one has to be careful about that. Second thing is that the constant force is not known a priori. So when you have to handle this, you don't know the nature of the constant force. So how you will handle this? So there this D'Alembert's principle comes, and in D'Alembert principle says that virtual work done by all force of constants are 0, and we consider static as well as dynamic situation, and then we express our coordinates in terms of independent variables q, which is the role of generalized coordinate, plays the role of generalized coordinate, and then we do this calculus, elementary calculus, to obtain the equation 14, which will be important for us to calculate this this equation 14 with the simplified version. So equation 14 and with this simplification. So in next class we will start with this equation 14, 15 and 16, and we will derive the equation of motion. So with this I will stop this class. So thank you.